All right, so how you guys doing today? Doing good? You guys had a good spring break?
I miss it.
Oh yeah, this is too short, right? I actually just drove back from Oklahoma last night, so it's actually 12-hour driving. When I got off of my car, I was shaking. It's quite a long drive. I don't know, but yeah. All right, so I don't know if you guys remember, we're still working on the chapter 4. And we're getting close to the last part of the chapter 4. So today I'm going to talk about the titration. So yeah, I wonder if it's already covered in the lab yet. Not analysis of okay. So I'll try to cover this one so you can have a much better approach in your lab when you're actually going to perform the experiment in the lab. Okay, so titration simply means you're trying to quantify. Or you can say find out the concentration of unknown concentrations of some solutions, or the solids, so the ions, by using countions. Well, what I mean by there's the ions and counter-ions in here, which we need to kind of recall from the previous lecture. So we're going to use a pH value to reach at the equivalence point. So this is the point. This is where we're going to have the numbers of ions and the counter-ions will be the same in number. So there be we're going to use this mechanism, this principle to identify the unknown concentration of your solutions, okay, using the ions and counter-ions. So here, obviously, we're going to use this one and this one, because the pH simply means what? The grid measure for your acidity of the solutions. So either you have an unknown concentration of this one or this one will probably tell you the concentration of your initial the solution. Okay. So I'll explain how we're gonna do this. Okay. So let's try to do practical case together. All right. So when you titrate the solutions, maybe we have HCl solution here. But the problem is you don't know the concentration. That's the question mark. So this is what we're going to solve for by just adding NaOH. So if you look at this one here, the HCl is obviously acid, which is normally provide what? Hydrogen cation in the water. So when it goes in the water, there will be what? Hydrated or solvated in the solutions. So they're going to actually give us these two ions, and one of them is the proton, which is hydrogen cation. This is why whenever you have an HCl solution, it will be very highly acidic. Okay, so this is our acid here. But obviously this one that has the sodium cation and hydroxide anion. So in the Arrhenius definition of the base, it is that compounds that give us the hydroxide anion. This is eventually grab one of the protons in the solutions, become water. So it actually neutralizes your acidic solution with this base. So whenever you have the hydroxide anion coming from the compounds, you can consider them as base. Okay, makes sense, right? Okay. Later on, once again, when we get to the Bronsted-Lowry definition, I'll talk about the hydronium cation And the one without the hydroxyl anion still can be a strong base. Maybe later this semester. Or are you guys taking Gen Chem too? You are, and you'll get there soon with this one. But for now, I think this is okay, which is Haynes definition. So anything that has a proton, hydrogen plus cation, or the hydroxyl anion, this will be two good contact to each other. So you can get we can get the used for the titration. So once again, pH will be the one that we measure. So here's the thing: whenever you have some device, pH indicator in your solution mixture, obviously if you have, here's actually one question I need to ask you. So if you have acidic solution, pH number wise, it will be lower than 7. You guys remember this? Right? So meaning if you have a HCl solution in your container, this will actually start at a very low position in the pH axis, or y-axis here, and then if you keep adding the basic solution, which is your sodium hydroxide solution here, obviously it will become less and less acidic, and will become passing the 7, and then now from there it will become basic solution. Okay, because you keep adding basic compound, which is sodium hydroxide over here. So this is the point that are meant by equivalence equivalence points. Okay, so if you pass this point, this is where you can assume that this one, okay, this is neutral. Make sense, right? Okay, does it make sense? Okay. So here's the thing. We don't know the concentration of this one, but we can always find out when it hits nearby 7. If you use some pH indicator that show you the change in color, you can use phenolphthalein and other methyl orange sort of thing. You can have some pH indicator that turns color of your mixture. Then you can say, when it turns the color of the mixture, you can say this one just passed the 7. The good thing about this one is here is you see the curve uphill and kind of less steep uphill, like kind of curvy line here. This part is very, very rapid, meaning you'll do this again in the lab. So from here, it's changing very slowly first, but it changed rapidly near 7 when it close to 7, and it becomes really quick, become basic. Even 1 or 2 drops makes this change so quick, so you can't miss it. Can you guys actually guess why? So think about you adding your basic solution into your acidic but somewhat we don't know concentrated solution, but here nearby the neutral pH will become really quick, because this is pH is what? Negative log of hydrogen cation. So the log is what? Power by 10. So if you get from here to here, the change can be rapid, the change even very small amount of the contact ions. So anyway, so whenever you see the change in color, you can say, this is now just about to be hitting pH 7 or just passing through over here. So for example, we said the initial volume of this one was maybe 20 milliliters, okay? And then we adding maybe 10, let's say 40 mils of NaOH was about 0.02 molar concentrated, okay? So when we're about to add about 40 in here, and you saw the color change, then that is where you can assume is nearby equivalence points, this is where you can assume or estimate the numbers of these two ions should be the same. So, meaning when it hits here, that is going to be, this is 1,000 milliliter to 1 liter. Okay, so this is the same as what? 0.04 liter. Okay, and then if you, this is what we learned before, 0.20 is a molarity is the same as what? Moles per liter. Okay. So if you multiply these two numbers together, the units for volume, the liter will cancel top and bottom, and you get the numbers in moles. Okay. So you have point. This is the 0.008 moles of NaOH defined in this solution over here. Makes sense, right? Okay. So if that is the case, if you have a 0.008 moles of NaOH, this is the same as just the NaOH becomes Na plus OH minus, right? So you can also say this is the same numbers of moles of NaOH of OH minus will be also there. Because this is a 1, 1, 1. So if you have a 1 moles of this one, you have a 1 moles of sodium cation and 1 moles of a hydroxide anion. If you have a 0.008 moles of NaOH, that is the same as in the solution, it's aqueous solution, as 0.0080 moles of OH minus as well. It's the same meaning, right? Because it's dissolved, right? Okay. So then once again, if that is the case, we're gonna do this one. Okay. So we have this is what we have. So we're assuming this should be also the same numbers here for counter ions, which is what? H plus. Okay? So to get these numbers of H plus, you need to have the same numbers of moles of HCl. Right? Because the HCl broken parts like this. Okay? So 1, 1, 1. It's the same. Makes sense, right? Does it make sense? So that means initially you had 0.0080 moles of HCl, hydrochloric acid, in 0.02 liter. Because this is 20 mils is equal to what? Right? Okay, so then you have this many moles of 0.0080 moles of HCl, okay, because we're assuming it's the same two, divided by 0.02 per liter. Okay. So then this is going to be all right, makes sense, right? We good? Okay. It's pretty easy, right? You just need to know. So let's do one more. All right. So the if you have a unknown concentration of HCl again, so we don't know the concentration. But initial volume was maybe 50 milliliter, okay? And now you add 20 mils of NaOH was in 0.1 molar concentrate, and then you saw the color change. What might be the initial concentration of HCl? Yeah, maybe 2 or 3 minutes, and we can do this together. So you have some unknown concentration of 50 mils of HCl. So you're doing titrating with your contact ion, which is the sodium hydroxide, especially hydroxide with the hydrogen. Then what might be the concentration here? Okay, 1 or 2 minutes. Okay, 1 minute. All right, so let's do this together. So this is where you saw the color change, which means this mixture will now somewhere near page 7. So at that point, we're going to assume that those numbers of the ions and contactors should be the same in numbers. So try to get the numbers of moles of this one first. So it would be 0.02 liter. Okay, this is once again, you just need to divide by 1,000. This is a unit conversion. So you have this numbers in liter now, so it's quick unit conversion for volume. And then you have the concentration was 0.1 molarity, which is moles per liter. So we just cancel the unit for the volume, so you can get the numbers for moles. Okay, so if you have this many moles of NaOH, this is the same as 0.0020 moles of OH minus. Okay? So if that is the case, we're going to assume the same number of moles of H plus hydrogen cation also there. So there will be, just copy the numbers right there. Okay. And then this many moles of the proton were there, meaning they also this many numbers of HCl. Because only one proton can be donated from one HCl. Okay? So we can assume there will be same amount of these two were there. Okay? So if that is the case, we can assume this many moles of HCl were initially in 50 mils. So we're gonna divide this one by 0.04 liters of it. Okay. Okay. So that will be approximately 0.401. So that makes sense, right? So the only thing you really need to know is try to get the numbers of moles of your contact ions. It could be the other way. I was looking for maybe NaOH here, HCl here, but the same. Try to get the numbers of moles of the contact ions for your titrating your sample. And then that number should be the same in your other ions. And then that number's coming from the how many compounds? One, then it's okay. Same moles of that divided by initial volume. They'll tell you your unknown concentration that you didn't know before you do titration. Okay. Make sense, right? We good? Okay. Alrighty. So you wanna do one more? Can I move on?
One more.
One more. Okay. Alright. Okay. So let's try to do NaOH. Okay? So you have an unknown concentration of NaOH. It's about 100 mil. Okay? So you have 100 mils of this, and you're titrating it the now HCl. This is also the counter to each other. We had about 50 mils, and then we know the concentration of your HCl was about the 1 molar concentration. Okay? And then, what about you adding about 50 mils? You saw the color change. What might be the what was the initial concentration of NaOH? Because you keep adding, the concentration will be already changed, but before you did, yeah, about 2 or 3 minutes ago. Okay, 1 minute. Okay, what's the answer? Perfect. There you go. Okay, makes sense, right? So same. So you just multiply these two together. So I'll put this in the liter. Molarity, you can get the moles. This is the same, and should be the same as HCl, right? And divide this by. So I just got the numbers moles of the HCl, and I assume there should be the same numbers of OH minus, and also same numbers of H plus, and also the same numbers HCl, because they were all 1, 1, 1, 1. And then initially it was in 100 mil, so it's the same as 0.1 liter. So I divide that number by 0.1. Okay. One more? Or can I move on? We good? Okay. So anyway, I'm going to do the more practical problems anyway before the exam 2, which is early April. So anyway, all right. So now we're actually done with the chapter 4. So we're getting into chapter 5. So chapter 5 is about the thermochemistry. Actually, thermodynamics will be also the another name. But thermochemistry, we're gonna learn about obviously something that is involved in heat energy. Okay, so whenever you do some chemical reactions, you'll see this chemical reaction will release the heat energy, or they try to steal the heat energy from surrounding. So we're gonna look at this the heat energy in terms of the chemistry or thermodynamics here. So technically, we need to start thinking about what is the energy in the first place. So what is the energy? What is the energy here? So energy is simply capacity to do work. Okay? So meaning if you don't have energy, you cannot do any work. So to do the work, certain type of work, you need to have energy. So energy makes anything that can do some work. Okay. So now, what is work then? What is work? Okay. What is work? So work is this is a bit of physics, but this is the force. This is the force, and this is the distance. So if you have a certain force to push or pull something to, so if you have a certain matter, okay? So for example, you can have 1 kilograms of steel ball or something. Okay? And then the steel ball was here, but I want to move it to here. So you actually moving it to other position. So that is work. So if you have a certain amount of force to push or pull to relocate the matter, which is something that has what mass and occupying a certain space in the universe, you move it to some other place. That is we define as work with a force. Because to do the work, you also have to have a force, and how much force you have will determine how far you can move it to and something. Okay, so this is the work. Then if you can move the stuff matter to the other position, that means you have enough energy to do so. Make sense, right? Okay, perfect. So the one funny thing, the thinking lab you can do in your mind is like there's like a really well fixed, like a heavy or fixed on the ground something really heavy object on the floor. You try to push so hard, but it's impossible to move. Then you're actually experiencing very what fatigue and like tiredness, but still you have done no work there. That's kind of ironic. But anyway, so this is how we define the energy. Okay, so in energy, we have 2 types of energy in general. I think you might already heard from physics. Have you taken physics before? This is the energy that were inherent to certain object or certain beings. Should be only classified as 2 types of energy. It's these 2. So this is the kinetic energy. And this is the potential energy. So this is a really famous analogy you have heard already in the past, that you have a certain matter on the hill, okay, and then this is located in a very high position here, okay, and so this is very high in potential energy. But when you roll the ball down the hill, they're going to accelerate because of the gravitational force pulling it. So then, instead of they having the potential energy going down, at the same time it will have some amount of kinetic energy going up because it's moving faster and faster. So when you get kind of the lowest position and do the same up and down, now you're getting more potential energy, but slowing down, lower kinetic energy, and once down, lowering the potential energy and kinetic energy over here. Okay, but in some, the initial internal energy, we call this internal energy, or inherent to this object matter is always the same. Okay, makes sense, right? You already saw this before, right? In some other, yeah. So this is one thing I want you to remember. Okay? And you're actually going to wonder what is this potential? Like, what do you mean potential energy? Like there's the energy plus low position, low pin. You don't have to know this one yet. Whenever you get to know something about the gravitational field or the magnetic field, everything, you get there sometimes. If you're doing anything with the physics or I think engineering, but anyway. So there's a couple things I want to talk about here, which is entropy, which is in the capital H, okay, over here. There's a couple more things I want to talk about is Gibbs free energy. Oops. This is in the capital Z, okay. And then you have entropy. This is capital S, okay. So there's the three things that we normally discuss in the thermochemistry, but most likely, most likely this one will be mainly discussed because it's thermochemistry. I will tell you about these two later in detail if it's needed on this chapter 5. But mainly entropy will be the one with the energy. Okay. So here's the thing. This entropy is just showing some thermodynamic function of heat energy flow. Okay. So we're gonna talk about the pressure and volume and how does it work with the work and then the heat energy itself, and all together expressed in the form of entropy. Well, now I'm saying something is kind of confusing you, but you'll get there soon. Okay, and then Gibbs free energy is this indicator of the spontaneity. Of reactions. This is normally indication of the actually change in delta Z. So if you look at the change in Gibbs free energy, will indicate if your chemical reactions is going to be spontaneous or non-spontaneous. Spontaneous simply means this one. Whenever you have two different reactants coming in together and doing some chemical reactions to make new products. If they do it voluntarily without any energy included, or they just do it automatically when they mix together, that we call spontaneous reactions, because we didn't do anything, but they just come together and making a new product, which is our one type of the chemical reactions. But not just these two reactants are coming into the same position, same place, but still not doing anything. But when you force them, we try to put a certain amount of energy into the system, the mixture, and then they're going to start doing some chemical reactions to make a new products. That is what we call non-spontaneous reactions. But this is a good indication. The change in delta Z or the Gibbs free energy change will tell you if your reaction is going to be spontaneous or not. So if your Gibbs free energy changing Gibbs free energy is negative, it will be spontaneous. If it's positive, it's non-spontaneous. So the entropy, I'm not going to talk it too much, but just the definition now here as to for previous two. Entropy, it simply means the degree of disorder. Okay, so you probably heard this term in other field of study like politics or economics or business or all different fields of study. But in chemistry, we talk about the entropy. It's actually quite simpler, very simple term we describe. So what I mean by the degree of the disorder is the how much they have in kinetic energy. That's kind of explains mainly about the entropy. So if you think about the matter-wise, you have the ice crystal of water, okay, in the container. You have a vapor in another container over here. And then obviously the ones in the solid phase, like in the ice, the H2O molecule cannot move well because they're kind of fixed in a certain position. It shows very uniform pattern of the arrangement of their positions of molecules in the crystal, ice crystal. So meaning it's almost guaranteed they will have very, very little amount of the motion inside. The only thing they can do normally is like a little bit of vibrational or a stretching type of molecular motion. But in a vapor, if you think about hot vapor in your container, obviously they show really big space among these all vapors in H2 molecule, gas molecules. They're going to move really fast and fully in the container. So in this case, we can say kinetic energy wise, this is a lot higher in here. So they can move really fast. Makes sense, right? So in this case, we can say this system now has much higher in entropy than this one. Okay? So this is very high in entropy. This is very low in entropy. Because if you have a lot of things moving really quickly and really long distance, you're always going to see there's no order. There will be less order of the position of the element or the molecule. But in here, you can see very uniformity of the arrangement, which will be very nice and high in orderness, which is the opposite of your entropy term. Makes sense, right? So this is pretty much only thing I want you to know for entropy. We're almost done. But there was from Wednesday, I'm gonna tell you how we're gonna use the entropy and Gibbs frequency. Not so much for the entropy, but from Wednesday we'll do this. So we only have a couple minutes, but I want to talk about this one. This is really famous. That's why I'm telling you this. Entropy once again is an S, okay, right? So we also use a change in entropy. Okay, so change in entropy. So if you change in entropy is positive, it means it's your product minus reactants. Okay? Is positive, meaning your entropy has been increased after chemical reactions, right? That's how you get the positive number and change in entropy. So that meaning after chemical reactions, you have a more disordered products than the ones in the reactants form. So that is the thing. But here's the thing: if that is true, you have this unit. You may see this one in the physics, especially on the astrophysics or other type of physics class. That this is represent the universe. UNIV is universe, and then this change in the total entropy in the universe, like in everything, is always positive. It's always positive. Okay, I want you to remember this one for any physics class. This is always true. So the entropy is always increasing in total amount-wise in the universe because we believe in Big Bang theory. So from the Big Bang theory, everything that is being kind of exploded from the one singularity point, and it means it's actually expanding the space total volume of the universe ever since we had a Big Bang. So in that way, the disorderliness of the universe always has to be increasing. So this is kind of this one. So this is actually coming from here. So you see this is a change in entropy of system. System means a very small reactions. Certain elements or molecules doing some chemical reactions. So that's a very small part of the universe. So this is system, which your reaction or any you define as a system. And everything else is surroundings. Everything else is surroundings. Okay? So except this system, everything else is just awesome. So the whole universe except your reaction is surrounding. Okay? That makes the obviously what everything which is universe is always positive. So this could be sometimes negative, but always in total has to be positive. So this is something. Yeah. All right, I'm just gonna finish today.